Okay, the final part of this series, I just want to quickly introduce another problem, which is about plate elements and also about adding point mass in your model. So, so in this problem, we're looking at this aircraft wing, which has a close to a triangle shape, and we're talking about the aircraft is adding a fuel tank at the tip of the wing and trying to discuss how that fuel tank can affect the natural frequencies of the wing. Okay, so because the wing is not skinny and long, so it cannot be modeled as a beam, but we can model that wing as a plate elements. So in the FEA as well. So just go back into our workspace, and we're starting with a model analysis. In this case, because in the question the wing is aluminum alloy, so we just want to add the new material to the system, and the general material aluminum alloy. General material aluminum alloy, and add it to our list. Then do you want to define your geometry? So in this case, you want to define it in a plate rather than beams. Okay, so the wing of the aircraft has been simplified as a right rectangle, so we can just draw rectangle. So the longer side, which is the side that's been connected to the aircraft, is 2.5 meters, and the other side, which is the span, is 1.5 meters. So now we have created a plate. Okay, so that's it. That's all we need. And close that, because you don't have to define your the thickness in this step. So go into the model. Okay, now we have loaded the model, and the first one we got a question mark here because we haven't defined the thickness. So we just define the thickness as given as 0.1 meters, 0.1 meters, and also we want to change the material because default is structural steel. I want to change it to aluminum alloy, and that's it. Then we have a look at the mesh. So we just generate the mesh. That looks might be okay. Then we need to define our boundary conditions. As mentioned, this longer side is the side that connects to the wing, to the aircraft, so it's fixed. And that's it. That's all we need. And we just add total deformation, aka mode shape, and we just want to set up how many modes we want to find. In this case, I'll probably put 10, and so. Okay, so now we get some mode shapes. Again, you can show the actual thickness of the aircraft if you want to. So that's the first mode. It's similar to the first mode of the beam as well. So, and it has a natural frequency of 61.35. And the second mode is doing like that. So it's become a little bit different to the transverse vibration of being. It has a nodal line. Now we call it a nodal line rather than a nodal point, because it has a line that had no deflection. And third mode. In this way, okay. So these are the mode shapes that we want. In this case, we probably only focus on the first mode. And in the question, we asked to discuss the effect of the fuel tank to the natural frequencies and validate using FEM. So we want to pretty much using Dunkley's method. If you remember Dunkley's method, there is something, the basics is firstly just look at the system without the tip mass only. That's we just have done already. And the second one is we want to look at only the tip mass and only the stiffness of the beam, so, or of the wing in this case. So we want to know the stiffness of the wing, and there's no way, or it's very difficult to analytically calculate that. So I just run in FEA, I can just simply run a static analysis. So I just add a static structure. So basically in this one, I'll just add a force, similar the fixed point. I'll just add a force applied at the tip of the wing, and I'll define a force in y direction. It doesn't matter how big the force is, let's say 10 kilonewtons. So it will just give you, and also I'll just add, I'll be looking at the deflection of that point, deformation. I'll look at the total deformation, and I'll also look at the directional deformation of that particular point in y direction as well. So in this case, we know the force we apply, and we know the deflection we have. Therefore, we can then back calculate the stiffness of the wing. Then when using the Dunkley's method, we can calculate that omega 22 by using the root k on m. So the k we can get from this simulation, and m is the mass that we add into. Okay, so that's the deflection of the system when we apply that load. It's just it doesn't move like that. It just the animation is repeating itself. So it's basically just apply the load and they move down, and that's it. And if you look at the static deflection, it's about 0.02 meters, or 0.02 meters. So it's about 1 millimeter, about 2 millimeters. So if you use that number, use the force that we apply, 10 kilonewton divided by that deflection, and we get the stiffness of the wing. Then later on you can use that to estimate the natural frequencies with the fuel tank at the tip. Lastly, we just want to repeat that, just validate. Hopefully you got some numbers on your calculation. So we just want to validate that. In order to do that, we just need to add that tip mass, right? So to add the tip mass, you just need to go your geometry, and there's a point mass here. And you just pick a point that you want to add the mass, and you just give the mass value. So in this case, it's 500 kilograms. Before we run, remember our first mode natural frequency was about 61.35 Hertz. And then we just run it again. Unfortunately, in ANSYS, those tip mass, adding tip mass has to be shared across all your simulations. So you will override the original data. Okay, so now we have some results. So the first mode from 65 become about 15 Hz. So it got significantly reduced the natural frequency of the tip wing. And obviously the second mode has been affected, and also the mode shape has changed significantly as well. Okay, so that's the last part of this series of videos. We had another example. We looked at how to deal with the plates problem. We also looked at how to do a static structural response to find the stiffness of the structure. And lastly, we learned how to add a tip mass to the system. Thank you very much. Bye.